Hello and welcome back to Earth Science. Today we're looking at chapter 3, which is on models of the Earth. We use lots of models to look at the Earth. The Earth is a very, very big planet. It's very, very hard for one individual to get out into space and look at it and study it. We've talked so far a lot about the beginning of Earth Science, and we've talked a lot about the tools and scientific process and how we actually get down to studying Earth. Now we're going to talk about models of the Earth and how we use them to look at it. The first and most simplest, you've seen it, it's a globe. They're three-dimensional models of the planet. They're awesome. You can spin it around. You can look at different places on the world. You can see different countries. You can see bodies of water. They're not really convenient. You can't pick up a globe and just carry it anywhere with you. You can't just put a globe in your backpack going to school. That would be the only thing that you could put in there. You can't just fold it up and put it in there. I always thought it'd be really cool to have a blow up one that you could just take out and blow up, but still not super convenient. So instead of globes, we can use maps, and these are flat two-dimensional representations of Earth's surface. And unlike a globe, you can just pick this thing up, you can put it in your pocket, you can walk away with it. You can take one out when you're on a road trip, you can have one in the middle of class, you can read one on your free time. Maps you can just take out. Now we're getting a lot more on our phones, and you can Google Maps. They don't depict the Earth as accurately in 2 dimensions. We have to kind of make some accommodations. It's like when you have an orange peel and you try to peel the orange and you try to get it all in one sheet and one solid piece. It gets these weird bumps and rips and tears in it when you try to flatten it out, and that's the same exact thing that happens when we try to take the globe, the Earth, this big round thing, and flatten it down. So who makes maps? Well, there are cartographers, is the official name for a map maker. And they've devised different ways we project the Earth in these 2 dimensions. And each of these projections, as they're called, have different benefits and different disadvantages. Some of them are really good for planning trips, and some of them are really good at looking at land masses. What you're doing and what job or end you're trying to accomplish will really determine what map projection you're going to use. So the first is the Mercator Projection. It takes the Earth, this big round ball, and it crunches it down into a cylinder and then rolls it into a map. And the nice thing about it, one big upside, is it projects all of the world on one map. It doesn't do very good when we talk about the polar regions, though. It makes the poles really, really distorted. And on this next slide here, I'll show you. It takes these nice poles, like the South Pole down here is huge. It is more landmass than almost the entire rest of the world combined, even though it's not that big. The South Pole does not take up this much space, but because we had to unroll it at the poles there, it does. Everything else, like the continental United States and South America and Africa and Asia for the most part, and Australia, all look pretty good. Greenland's bigger than it should be. The South Pole is much bigger than it should be. So it does well in the middle, but not so much on the poles. Our next one is a nomic projection. Think like garden gnome, like nomic projection. And this is a planar projection, and it's looking top down at a region of the planet. And it's usually used to look at the poles, and it accurately shows the shortest distance between 2 points. But it does distort land masses shapes away from their center point. It's very useful for planning ocean or air voyages. If you're going to become a pilot, if you're going to be looking at flight plans, a lot of times they're using nomic projections. On the next slide, I have a picture here. We're looking down at the poles in the center here. Like Greenland is now the right size, and all the poles are here. It's showing these very accurately, like in between here, in between Alaska and Russia here. But as we move further and further down, Mexico and Baja California are getting really, really big. Parts of Europe are getting a little stretched. In these first 2 circles here, first 3 circles really, it's pretty true to form, but as you move further away from this nomic projection, it gets less and less accurate and more distorted. Something also to notice here, this is a small piece of the globe. We're missing all of Africa, well, other than the tip here. We're missing most of Africa and Australia and South America and Antarctica are all missing off of this map. So some pretty big downsides to using a nomic projection. Polyconic, this is our last projection we're going to talk about. And this is if we take a cone and we roll it up and wrap it around the Earth. In this one, the lines of latitude and longitude are curved. Most landforms are the correct size and map. And this is really useful once again for looking at the middle latitudes, kind of like the Mercator projection was. On this one, it's the Antarctica is closer to the right size. Greenland and the poles are a little distorted because we had to, like you're cutting open an orange, like you're trying to peel an orange, distort this kind of part where it would wrap around. The oceans look huge. The Pacific is not this big. It looks that big. It's not that big. But things like Africa in this picture are the right size, and most of Asia and South America. As we're getting down closer to the poles, it starts to distort very quickly. Like Australia is huge on this map. It's not that big on the real globe. The top of North America is getting stretched out. But things right here in the middle latitudes, they're pretty a-okay. They're pretty spot on. So when we talked last one, we started talking about these imaginary lines of latitude and longitude. These are what we use kind of like the same way that your mailbox has an address. Latitude and longitude gives us an address for spots on the globe. The Earth is divided into halves. We call these hemispheres. There's a north hemisphere and a south hemisphere, and an east hemisphere and a west hemisphere. The equator is this middle line in between the north and south hemisphere. It's at 0 degrees latitude. The prime meridian is the one that we use to split it into east and west hemispheres. Equators north and south, prime meridians east and west. There's a 180 degree meridian on the opposite side of the planet from the prime meridian. The equator is really nice. It goes all the way around the globe. There's no mixing it up for anything else. But the meridians are a little bit weird. There's the prime meridian, and then there's the opposite. There's a 180 degree meridian. So for latitude, think latitude, fatitude. It's going around. The equator goes all the way around. There's the 30 degree line, the 60, the 30. Up here in North Idaho, we're closer to the 48th parallel. Latitude, the equator is our middle line of latitude. It's the one we start from. We also call latitudes parallels. So if you hear about the 45th parallel or the 48th parallel, and that's because these lines are running parallel to each other. We measure them in degrees north or south of the equator. The equator starts at 0, and then the minute you start moving more north, you go 15 degrees north, 30 degrees north, 60 degrees north, all the way up to 90, which is the North Pole, 90 degrees north. And on the other side, you go 15 degrees south, and 30 degrees south, and 60, all the way down to the South Pole, which is 90 degrees south. Longitude, they go up and down on the map, and they're getting bigger on either side of the prime meridian. The prime meridian is the one we start on. It's our main line of latitude. We also call longitude is called meridians. So when we talk about time meridians, we're actually talking about lines of longitude. They run north and south, and they connect the poles. We measure them in degrees east or west, and the 0 degree line is actually running through Greenwich, England, and that's a really important fact. There's lines painted in Greenwich about this line going through there. It's really, really important when we start talking about time zones. Each degree of latitude and longitude, there's 90 in between the equator and the North Pole, and each of those go up 1 degree. In between each of those 1 degrees, there's 60 minutes in between the lines, and in between each 60 minutes, there's 60 seconds. So the same way that we can say 5 miles up, Alder Creek, we can say 5.5, 5.55. We're just getting a little bit more precise about where in the world we are. Map scale is really important. Every map that you look at is going to have a scale on it. What size is, how does that actually measure up to the Earth? So the scale of the map tells you how the map's features compare to the Earth size. Is it 1 inch equals 2 miles? Is it 1 inch equals 5 miles? Are you looking at a bigger area? We usually see it as a ratio. Like I said, 1 inch is 1 mile, 1 inch is 2 miles, 2 inches is 70 miles. You can go all the way up to really big numbers. On this next example here, we have 1 inch equals 1.576 miles, which is a really weird, kind of very specific number. But sometimes they get weird like that. It's just whatever size map you have, that's the map scale that they're going to have. This one's just showing the bottom half of the country and even the bottom corner. If we were to go the whole country, to get it on the screen, we would have to do 1 inch is equal to, maybe several hundred miles. So maps are not always oriented with north at the top. So to find out what's going on, you're going to look for this compass rose. And sometimes this is really simplified, and none of this is here except the north, just pointing north. And whatever way is pointing north, then you can find out that east is going to be on your right, west is going to be on the left, and south will be running straight down opposite of north. So map making is an old thing. We wanted to find our place in the globe and kind of figure out how to get to and from places really early on in human history. One of the first known maps was on a clay tablet in Sumeria in 2300 BC. Once again, this information here is going to be important. And map making is constantly changing and has changed so much in the last 70 years as new technologies have been discovered. In 1879, we had the United States Geological Survey. This is where we started looking and trying to describe the United States on a map. We created our first map of the United States was in 1879, and it was founded for the purpose of classification of public land, very much tied to surveying things and making sure we knew exactly what the property looked like. We used a very classical mapping technique called plane table surveying, and plane table surveying is interesting. In plane table surveying, you had a drawing board here, like this guy's got here, and you had this site on it. And he would carry this picture's kind of misleading because it looks flat. He would carry it to the top of a mountain and then draw whatever he or she could see. And usually, if you've ever sat down and tried to draw something, drawing a map at that level, trying to draw an accurate map, takes a long time. And using this sighting device was very difficult. So there's some big disadvantages to using plane table surveying. It took a long time. It was very time consuming. Cartographers would have to brave cold weather, bad weather like rain. There's reports that they had to deal with bandits and horse thieves. They'd come back down off the mountain and their horses were gone and they had to walk all the equipment back to town. And map makers had to have a great amount of skill. There was definitely better map makers than others. And to be one of the best ones, you had to have a lot of skill. So it was very quickly that technology started to change map making. And the first kind of upgrade we got was planes and using photography. So now we could take pictures from way up high, and we were doing a lot more surveying. So adding in this information from the ground and then having these pictures from above meant that we could make much better maps. And you could make much more accurate maps because you had a picture of it that you could take back, sketch, whatnot. The con to planes and photographs was at first it was pretty expensive, and secondly, it wasn't useful when it was cloudy. If you had a rainy day, you couldn't go fly the plane because you couldn't take a picture of the ground. We then upgraded again and got radar, and now we could use radio signals. We could bounce these radio waves off the Earth. The same way that we use sonar to map the bottom of the ocean, we could now use radar to map the surface of the Earth. Nice thing about it is you can shoot radar through clouds. It doesn't matter what the weather is. You can use radar any weather. The cons is now instead of being able to see it and a human interpret the data, we now needed the data to be interpreted by a computer. In 1972, the National Aeronautics and Space Administration, NASA as we call it today, launched the first Landsat satellite. This is Landsat 1. We've had Landsats 2, 3, 4. I think we're up to 5 or 6 now. And what this does is it detects different wavelengths of light bouncing off of the Earth. The cons to this is the images don't appear in real life color. So we have to actually use computers to create a false color image that produces something that our human eyes like a little bit more instead of blacks and whites and grays. In 1999, we started the Earth Observing System, the EOS. And instead of looking at images of Earth, we're tracking Earth's processes. We're looking at the carbon cycle and the water cycle and the nitrogen cycle. And we're taking precise measurements of air to land and land to sea exchanges of these energy, carbon, and water. This gives us a lot more information that we can use for predicting weather and seeing trends in farming and seeing how much carbon emissions are being put out into the air and where in the world that the most energy is being created and used. Very cool things that we could actually track Earth's processes and get some more information about the whole system and not just a picture of it. Another piece of technology that we really like, you probably carry it around and use it in your phone, is the GPS, the Global Positioning System. This allowed people to determine their speed, position, and time anywhere on the world, regardless of time, temperature, or the weather. There's three parts to the GPS. There's the space part, the control part, and the user part. And we're going to talk about each of these in a little bit more detail. The space part, there's 24 GPS satellites. And at any time, anywhere on the Earth, there's 5 to 8 of these satellites visible at a time. So there's lots of satellites. These satellites are positioned in such a way that they have access to the entire surface. The second part is the control. There's a master control station near Colorado Springs, in the United States, and there's 3 ground antennas and 5 monitoring stations around the world. And what these do is if the satellites get out of position, we readjust them, make sure that they get back into the right place. We adjust their orbit to make sure that they stay in orbit and that they stay where they're supposed to be. They're in geosynchronous orbit, so we make sure that they stay where they're supposed to and that they're functioning properly and have the proper software and programming to stay functional. The third part is without all this, with all this information, you need to be able to use it. You, the user, are the third part of the GPS. You pick up the broadcast, you need at least 4 satellites, and with this information you can determine your location, your speed. It's not affected by bad weather. It works when it's cloudy, when there's lightning. It's above Earth system, so it doesn't, Earth system does not interfere with it. A popular game is geocaching. This is where one group or individual will hide a cache, an object to be found, and others will try to find it using the GPS coordinates. Usually there's other hints that go into it and stuff like that. There's still people that do this today, and they've made very intricate ones or very simple ones. It's kind of a fun activity if you ever want to get into it. Something that we use a lot in science, in all the sciences, all disciplines. Biology uses this, earth science, any kind of meteorology is using the Geographic Information Systems. This is the GIS. And this combines all kinds of data from satellites, statistical surveys, land surveys, wildlife surveys, schools of fish. We're displaying information such as land use over time, what terrain looks like over time, what weather looks like over time, looking at migrations of rabbits in a field. I mean, there's a lot of applications that you can use the GIS for. One of the things we're going to spend a lot of time in the second half of this lecture is we're going to talk about topographical maps. And they show the topography of an area. And the topography is the natural and man-made features based on their elevation. We call this relief. This can be shown through shading, but most of the times we use contour lines. And contour lines are these narrow lines on a topographical map that indicate elevation. At an area of sea level, the elevation is 0 feet or 0 feet above sea level. And then each line that you move up, you're moving up a certain interval of elevation. And all of these lines on a topographical map, much the same way that a map scale, like every inch was worth 2 miles, all of these lines are going to be the same height. So if one line's going up 10 feet, every line is going to be going up 10 feet. We call this the contour interval, and that'll be usually labeled on whatever map you're looking at to kind of give you a guideline for what those lines on that map mean. Usually, not every line on a topographical map will have a number next to it saying the elevation, but every 5th line will be a darker, bolder line, and it will be labeled, and we call these reference lines. Another type of topographical map you might run into is a topographical / bathymetric map, and this shows both the land and water elevations. So it shows how high the land goes and how deep the water goes. Isobaths show the form of the land under the water. Usually this part of the map will be blue, so you can see that it's probably going to go down as you get towards the center of it. Another part of this that we look at is slope and elevation. The distance between contour lines shows you the slope or steepness of the landscape. If the lines are far apart, the land is flat, and if they're very close together, if these contour lines are very close together, that means you're going a lot of elevation very quickly. And I'll show you an example here on this slide. So for these 2 different examples, this one on the right here, these lines are very far apart. And so what you see is this very slow, gradual kind of rise in elevation here. Where on this side over here, where there's a lot more lines, so we're getting higher, and they go up very fast, like these lines are very tightly packed together, this is a much steeper slope than this one, where these lines are very far apart. Remember that each one of these lines go up by the same amount, so if this is 10 feet, this would be 1440, 1450, 1460, 1470, and we can see that that's about right. 1450, 1460, 1470, 80, and 90, so this one should be about 20 feet higher if we're going by feet here, and it looks to be about that. So how do you find slope of the lines? To determine the slope, you're going to divide the change in elevation by the distance covered. So elevation 1 will usually be your big distance. Like let's say, for example, you're doing, I have a mountain that is, let me find my pin here. I have a mountain that is 1450, and I'm starting at the base, and it's 1400 feet. And I know that I have to go 2 miles. To solve this one, you would subtract the top minus the bottom, and you get 50 divided by 2. And then you end up getting 25 feet over 1 mile. So that would tell you that every mile you'd be going an elevation change of 25 feet, which isn't bad. That's not a very steep climb. If it was going from 0 to 1450, it would be much more severe and much more extreme of a slope. But that's kind of an example on how you would find a example problem of one of these. Oh, and here's another example. Okay, so we are standing on a mountain at 1,400 feet above sea level, and we see on our map that the peak across from us that we want to go up and go to is 3,165 feet above sea level, and that the distance between us is 2.5 miles. So how do we find this slope? Well, if you want to pause it and do it before I give you the answers, you could do that now. I'm going to work through it. We'll do it in green this time. So we take our higher slope, 3,165 feet minus 1,400 feet divided by 2.5 miles. And we're going to end up getting 3,165 minus 1,400 it's going to end up being 5, 0, 7, 1, 1,705 divided by 2.5 miles. And I'm actually going to cheat real quick and use my calculator. You guys can use your calculators as well when you're using these ones. You're not going to have to do these ones mentally in your head. And then our answer is going to be 1705 divided by 2.5. So it's going to be 682 feet per mile. So that one's a much steeper slope than the last one we did. But there's another example on how to do one of those, a little harder one. So a benchmark, if you've ever been out hiking in the woods and you found a brass or aluminum plate, this is probably a benchmark. These are permanently set in the ground, and on a map they're shown by the abbreviation BM, and they'll have either a cross, a triangle, or an X on them, and then BM written above them. And these are like just positions on the globe where we've put these marks so that cartographers can go and surveyors can go and start there on something they know and then figure out everything else around it. So, there's lots of topographical map symbols that will be used. The peaks of a hill, like if you're at the very top of it, the very top even if it's not like a regularly scheduled contour line, will have its elevation there. And if you have a circle or oval with small lines jutting inward like this, that means that you're going to have a depression there. It's going to be going down instead of up. And we call this a depression contour. An example of this might be like a dead volcano. Like if you have it's going down here instead of going up, each one of these little lines is going to have these depression contours on it. As you're moving down, those same increments is normal. For your bodies of water, they're always going to be in blue. Lines crossing a river are going to point towards the source. So if you have a river running from a lake, like when these lines cross, they're going to be pointing towards the source, back up the hill. Human-made features are going to be depicted in black. So if you see a grocery store, it'll probably be something like this. And if we have like an area that has a lot of people or settled regions, but we don't want to just depict all the human things in it, it will be like shaded just pink. So our topographical compass rose is going to point towards magnetic north, not true north. If you remember from your physical science in middle school, true north and magnetic north are not the same. They're a little bit, different from each other. Magnetic declination is the angle that the compass needle will vary from true north. This differs from where you are on the globe. It's different on the equator than it is for up here, than closer to the North Pole. And this angle will be located on your compass rose, so you can find it there if you ever need to figure out what the magnetic declination of something is. You won't for the scope of this class, but if you ever wanted to when you were using one, you would know how to find it. So for using topographical maps, you can determine the shape of the landforms looking at a topographical map. So if you have a feature you're interested in, let's say, for example, we have the top of a mountain, and it looks something like this. Where it's starting at 1500 here, and each one's an extra 10 feet. We can figure out the heights of all of these different lines. Like if I was to draw a line going from one side to the other, we could figure out what that should look like. So we draw a graph showing elevation, start at 1500, have 1510, 1520, and then that one looks like it goes up to 1530 there at the peak. And here at the beginning, it looks like those lines are pretty, like if I go to this line here, we're going up to 1510, then we go up to 1520, but it takes us a little bit longer to get there, so we're a little less gradual, more gradual. And then from here to here, it takes even longer, so we're even a little more gradual to get up to the peak there at 1530. But then on the back side of this, like all of these are really close together, and we go right back down to 1500. So if we start at the top here, 1530, 1520, 1510, 1500. These lines are all one line, so we can tell that this whole bottom here is 1500. So what that would show us is that this backside of this mountain looks like this. Like very much steeper than this front half here. That was much more gradual. And so using these, you can like kind of scope out and like if you were looking at it from the side, what would that landform look like? And using this information, it gives you all kinds of applications. Like maybe you know that you want to hike this more less steep side. That's the side I want to go up, and down probably. I probably don't want to go down this backside, but it tells you all kinds of information about that. You can use it before you go out on hunting trips, before you look at hiking, if you're just going out to explore. Like if you want to look at like building a building somewhere, you would want this more flat side than you would want this steeper side. So they give you a lot of information. This is the end of chapter 3. I hope you have learned a lot this chapter. It's very, very cool to see how these different ways we map the Earth and to get some practicality and application that you might actually use in your life. That's pretty cool. If you have any questions, let me know, and I hope you enjoyed.